All right, so let's continue. So this bottom-up approach is original from this sigmoid. Sorry, not sigmoid. Sigmoid 99 paper. So sigmoid is the top tier conference in database area. Right. So the idea is to compute the cube from bottom to up. So if this is the structure, this is the lattice. They start from the bottom level and from bottom to up to do the computation. So the essential idea is to use divide and conquer, or more specifically, to use recursion. Right. That's why I mean, when during the during this class, when we introduce the idea and the procedure of this BUC, you probably cannot feel why it is bottom up, because everything when we do the explanation, it seems that we do it in a top down in a top down way. Okay. This is because naturally, I mean, you cannot really do it bottom up. It is my own understanding, because for the bottom, all you have is a 0D cuboid, right? And if you really do bottom up, you need to decompose this cuboid, which is impossible to some extent. So the real idea is to using this kind of a recursion idea. Well, if you know recursion, well, you should know it from 9021, I guess. So basically, in order to compute this OR, you need to have at least one of A, B, C, or D, right? And in order to have to compute A, you need to have at least one of A, B, A, C, or A, D, and so on and so forth. Okay, so it looks like a bottom up because we start from or if you look at the code, we actually directly compute the whole lattice, or the last, or say the last level. Okay, but essentially, I mean, in order to compute this 0D, we need a 1D. We need a 1D cuboid, and in order to compute 1D cuboid, we need a 2D cuboid, and so on and so forth. Right. So you probably just wait till the very end to see why it is a bottom up, approach. But just try to follow my instruction and to get the idea of this whole thing first. All right. And also in this course, we're introducing a simpler version. Okay, we're introducing a simpler recursive version. That's why it's called BUCSR. Okay, and this table, this figure is actually from the original table. Original paper. It's not that intuitive, so we kind of ignore that. Yeah, let's go to the next page. Yeah, let's go to the next page. So before we introduce the detailed algorithm of BUC, let's try to help you to review the recursion first. Okay. So recursion is a powerful computing and problem solving techniques. So the idea is, so let's start from the example here. Okay. Say if we want to compute the factorial number, we know that the factorial of n actually equals to n times n minus 1 times n minus 2, and so on and so forth, right, until 1. So basically we will have n integers here from 1 to n, and then we do the multiplication. Okay, but if we write this factorial into this form, say essentially fn or the factorial of n actually equals to n times fn minus 1. Okay, this is because if you take this part, it's actually the factorial of n minus 1, right? And if you times n, you will get the factorial of n. So this form, or this formula, actually gives the relationship between fn and fn minus 1. And this is usually called a recursive step. Okay, this formula is usually called a recursive step. So from Wikipedia, it's a set of rules that reduce all successive cases towards the base case. So what is the base case? Because you can think of, if we know that fn equals to n times fn minus 1, of course. So say if you want to compute n equals to, for example, f3, okay, it's actually equals to 3 times f2 equals to 3 times 2 times f1. If you keep doing it, it's 3 times 2 times 1 times f0, and 3 times 2 times 1 times 0 times f minus 1. But I mean, really, the problem here, because we have a 0 here, isn't it will make any fn equals to 0, right? Because 0 multiply anything equals to 0. So the problem here is that this recursion have to stop at some point. And this stop point is decided or defined as the base case. So we need to know where we can stop. Otherwise, we will do the recursion again and again. The stack is become longer and longer, and eventually, I mean, it is endless. So it must end at some point. That is called the base case. Okay, the base case. So for example, for this factorial thing, the base case should be n equals to 1, right? Because the factorial of 1 equals to 1. Or we know that factorial of 0 equals to 1 as well. But well, I think it's better to define factorial of 1 equals to 1 as the base case in this example. Right? Then we know that we actually can stop here, and we don't need these two parts. Okay, they're incorrect. And we know here should be 3 times 2 times 1, which is 6. So always remember, for a recursion form of the problem, you actually formulate the problem as a recursion. Okay, you need to have two things. One is a recursive step. The other is a base case. You cannot miss any part. You must have these two parts, right? So whenever you try to formulate a recursion problem, remember you need to decide these two parts. So if we take another example, which is quicksort. So basically, we want to sort a list from x1 to xn, and let's say we have no idea how to do the sorting, okay? But what we know is we can compare. What we have is we can compare the value of two numbers, right? To see if, for example, x1 and x2, we are able to know whether x1 smaller or equal to x2, or x1 is larger than x2. Okay. And the idea of quicksort is actually divide and conquer. So we don't know how to sort this kind of long list or long array. But what we know is we can compare two numbers, and we know that if the list contains only one element, then we don't need to sort it, right? Or say the sorting result of this list with only one element is itself. So this is the base case. So basically, base case is the usually is the most intuitive or most easiest or simplest case. Okay. So this is the base case of quicksort, and the recursive step, right? We need to somehow reduce the current problem into into sub-problem or sub-problems towards the base case. It's like reduce the difficulty or reduce the complexity, right? For example, if we now we are considering do the sort of a list, right? So what we're trying to do within this recursive step is try to reduce the sorting of a long list into a sorting of several short lists, right? So we take a pivot, we actually take any number as a pivot, and we divided the list into two parts based on whether x is smaller or equal to pivot, or x is larger than pivot. Then we will have y's and z's. So these two are the two shorter lists. Okay, and yeah, so we can sort these two lists separately, and then we just concatenate them together. We will have the sorted list because we use the pivot. So everything in ys should be smaller or equal to anything in this. So that is the idea. Okay, and in order to do sort y's, or in order to sort this, we can recursively apply this quicksort function. Okay, until we reach the base case. Okay, so I think these things have been introduced in other courses, so I won't go very deep in these cases. But the message I want you to take away is that in order to formulate a recursion problem or a recursion solution, you need to decide what is the base case and what is the recursive step. Okay, just these two things. And probably one more thing. Okay, here is another example. In this example, I try to show you what is a good recursion and what is not a good recursion. Okay, this CNM represents the combination of m objects from a set with n objects, right? So it's sometimes written as this, or in for the students from China, it's usually written as this. Okay, so they are all the same. So basically, you take m elements or m objects from a set of n objects, and these are the total number of possible combinations. Okay, so here here we use balls as an example. So basically, it is the number of ways to select m balls from n numbered balls. Okay, so these balls should be different, otherwise you cannot distinguish them. So what we want to show here is the recursive step. Right? So the recursive step is CNM equals to say n minus 1 m minus 1 plus say n minus 1 m. Right? So let's use an example to show the correctness of this recursive step. So basically, let's assume that m equals to 3 and n equals to 5. And considering any ball in the 5 balls, because if we number these 5 balls from A to E, let's consider D. Okay. Sorry. Let's consider D. Okay. So there are 2 conditions. Right. So one is that we have taken D. Okay, because we need to select or take n balls, 3 balls. So let's say we have selected D already. All right. Then we have to select the another 2 balls from 4 balls, because now we have A, B, C, and E left. Okay. So we need to select 2 balls, which is m minus 1, from 4 balls, which is n minus 1. So for this part, it should be C of m minus 1, n minus 1. And if D is not selected, then we have to select 3 balls from A, B, C, and E from 4 balls. Okay, so it's C of m, so still m, because D is not selected, and n minus 1. Sorry, I actually I've it should be n minus 1, m minus 1. Here should be n minus 1, m. Okay, and these are the 2 conditions. And if we sum them together, it would be the total number of combinations for selecting 3 balls out of 5. Okay, so this it's not a formal proof. Okay, it's not a formal proof. It's just to show you that this kind of recursive step is true. Okay, is correct. It is actually non-trivial to find the base case of this recursion form, but I will leave it to you to as an exercise or whatever if you are interested. I mean, it's not the key point of why we put this as an example here. The reason I put it here is because, say, now let's consider C n minus 1, m minus 1, and C n minus 1, m. So in order to compute C n minus 1, m, we actually need to compute C n minus 1, n minus 2, m minus 1, and C n minus 1, m minus 1, right? According to this formula. And you can see that this part, the C n minus 1, m minus 1, actually equals to what we have here. All right? And if you have ever written a code for this kind of recursion problem, or if you ever try to execute a program, you will see that this C n minus 1, m minus 1 actually have or will be computed at least twice. Well, it is twice in this case, but we will see n minus 2, m minus 2, which might be computed even more times. But anyway, the idea is that okay, there are some parts that are computed repeatedly. Okay, and each time when we do the computation, we need to apply the recursion function on top of it, and this kind of computation is a waste of time, because we can only do it once, but we choose to do it multiple times. Okay, so it actually increase the time complexity of this program. So this example tells us that we should try to avoid duplicate computation within this recursion formulation of or this recursion computation. Otherwise, I mean, if you know, actually every recursion form can be there is an equivalent. So there is an equivalent induction form for every recursion form. Okay, for example, we probably don't use this example, but for example, for the factorial number, right? We can do it inductively. Okay, we can start from f1, which is 1, and we know that so fn times n plus 1 equals to fn plus 1. So we can from f1 to compute f2, f3, so on and so forth until we get fn. So it's an inductive way of doing it, right? So if the recursive formulation we've formulated involves this duplicate computations, we should consider using the inductive way. Okay. And later we will see why we say BUC is a good algorithm, because it actually avoid of this kind of duplicate computation. Okay, so every case or every cell is computed just once, so there is no waste of time or no waste of computation. All right. So the key points here: the subproblem need to be smaller so that a simple trivial boundary case, which is a base case, can be reached. For divide and conquer, there may be multiple ways the entire solution space can be divided into disjoint subspaces, each which can be conquered recursively. So that's essentially what we have been discussing before, right? So now let's look at our problem. If you still remember, we try to compute the lattice of the cuboid from given the base case, or given the detailed fact table, right? So in this case, in this example, it's A1, so it's this white part. Okay, this white part is what we have, and what we want to have, or we want to compute, is the yellow part, the green part, and the blue part. Okay, so this is essentially a 2D cube, and we want to reduce it to 1D. All right, so okay, so this is what we do. We have this white part initially, and for the first step, we want to compute, when it's B, because for each cell it corresponds to A1. For example, here is corresponds to A1, B1. So for first step, we want to compute the cell corresponds to A1 and star, or star actually represents O here. Okay. So this is trivial because it is just an array, and we just do the aggregation. We do the sum by default, but we can apply other aggregate functions. Okay, so it is trivial to get this value and this value as well. So this is the step 1. So for step 1, essentially what we're doing is we do all slice on A, and then do the aggregation. Okay, by doing slice on A, we just take each and every value of A, right, and do the slice, and then do the aggregation, compute this cell, right. Then for the second step, we actually want to compute star B1, star B2, and star B3, where this star means on dimension A, it takes all. Okay. So in order to do that, we simply plus M11 and M21 to get this cell, and so on and so forth. Okay, this is the second step. And the third step is to get this value. So in order to get this value, we simply do the aggregation of the green values, and then we can get this blue value. So this is a 2D case, and it is sort of like a base case, okay, in this BUC algorithm. Now let's look at the 3D case, okay, where we want to reduce the cube in 3D to cube in 2D. So assume this is what we have originally, okay? This is the 3D cube, and for each, if we do the slice on A, right? If we do the slice on A, we will have a cube like this. So essentially, it is a 2D. It is a 2D cuboid, okay? Because you just take. This is because for A we have only one dimension, so you can take another angle to view. It is essentially a 2D cube or cuboid. And for 2D cuboid, we actually know how to do it, right? We have discussed this here, right? So given a 2D cuboid cube, we know how to say compute the rest part, which here is the yellow part. Okay, it's the yellow part. So for each slide, slice in on the A dimension, we have as long as we apply the algorithm for the 2D cube, we can have this, and this is essentially here, like this. And in this example, we have for A we have two values, right? So we will have this two slice, extended slice if you like, and we put them together. This is what we have for step one. For step one, and for step two. Okay, so you can imagine. I mean, eventually, what we want to have is something like something like this. Okay, I'm not drawing it very good. So basically, it's the green part. Okay, it's the green part, and then the blue part. The reason that, okay, because some of you may argue that you can, for example, we can get this green part by say applying a slice on B, for example, right? And you can imagine if we do the slice on B, and then for each of the 2D cube here, we can actually apply the similar technique to do the expansion, right? Then we can have, of course, the green part, but also the part here, and perhaps another cube, another cell, another two cells, in fact, here and here. Okay, I'm not sure if you can understand what I'm saying, but essentially this is not good, because as you can see, if we do something like this, if we do the slice on B and then compute or reduce the 2D cube to 1D, we will compute these four cells twice, at least twice. So this against the designing rule that we have mentioned before, say we don't want duplicate computations within this recursive processing, right? So that's why it is not a good idea. We just want the green part. We don't want anything overlap with the current yellow part. Okay. So essentially, what we're going to do here is just remove dimension A, or take dimension A as all. Then we can have this green part, and as long as we have the green part, it is similar how we get the blue part. The blue part, as it is just it is just a reduction from 2D to 1D. Okay. So for a 3D case, still 3 steps. Okay. One is to do the slice on A, and for each 2D cube, do the reduction to the 1D cube, and then put them together. We have this yellow part, and then we remove dimension A, or say collapse the cube from 3D to 2D on dimension A. We get this green part, and apply again the from 2D to 1D. We can have this blue part, and put them all together. We will have this cube, which is the answer that we need. Okay, the answer that we need. So if we look at the pseudocode, it's something like this. Although there are some incomplete parts, for example, the output is incomplete. You need to fix this by yourself. Also, this is the BUC SR algorithm is what you need to implement in lab 2. Okay, in lab 2. So basically, the boundary case, or the base case, is where data is essentially a list of measure values, or say the dimension is empty. Okay, the dimension is empty. So basically, just output the sum of the data. And for a general case, what we need to do, we need firstly slice on the first dimension. Okay, of course you can choose to slice on other dimensions, but in order to make the algorithm run correctly, it's better to, because the dimension is somehow ordered. At least, I mean, implicitly ordered within a list, right? So every time we just take the first dimension and we do the slice on the first dimension. So for each of the distinct value v of dimension 1, we do the slice, and then we apply BUCSR on this slice and on the rest of the dimensions. Okay, so for the rest of the dimensions, the dimension 1 is excluded, right? And okay, so this is the first recursion function that we call, and then we do the project of data on rest of the dimensions. So basically, we project out dimension 1, right? In this case, so this is how we get the green part here. Okay, the green part here. We get this data prime, and we apply BUCSR on data prime and the rest of dimensions, because as you can see, I mean, this green part essentially has very similar form, or essentially the same as these 2 slices in the first step. Okay, these 2 slices in the first step. So we apply the same technique, or the same algorithm, or the same function on top of it. So it's BUCSR on this data prime, and still on the rest of dimensions. Okay, and as you can see, because each time we call a BUCSR on the rest of dimensions, so dimension 1 is excluded. And then for the rest of dimensions, we will recursively exclude the first dimension until the dimension is empty. Okay, so the algorithm can stop correctly and can output what we need, right? So this is another example. So basically we have here, it's a 2D example, right? You need to build your own example for 3D. Actually, it is very important that you do this, because it will help you understand the whole algorithm, such that it will make Lab 2 much easier. All right. So let's look at the 2D example where we have 2 dimensions, A and B. Okay, and we have the measure M. If you still remember, this is what we expect to see. Yeah, something like this, right? Something like this. And later you will see how we get that. So for for this 2D example, we first do slice on A, right? So A have 2 distinct values. One is 1, one is 2, right? One is 2, one is 1. So this is the first slice. Okay, this is the first slice where A equals to 1, and this is the second one, the second slice where A equals to 2. Okay, then we actually have this internal output where we do the computation. So for first slice, we have B. We kind of do the do the group by on B, and then do the aggregation again. So we have B equals to 1, 2, and 3. Here the number should be 30, 30, and 40, and also here the last line would be B equals to star, which represents all, and M is 100. Right. So the actual output, we would put A back. So here A is all 1. Okay, and for the second slide, we have B equals to 1, M equals to 50, and to sum up them together, we have B equals to star, M equals to 50 again, and put A back. This is our output. And for the third part, is when we reduce on dimension A. So we have when B equals to 1, the M is, so we take all B equals to 1, the sum, the M is 80. Okay, B equals to 2, M is 30, B equals to 3, M is 40. Okay, and then for the internal output, we do a aggregation again. We would have 150. So remember here, if we have A here, A should be all star here, right? So that's why the output, A is star, and B is 1, 2, 3, and this the last line where A and B all both are star, or all in this case. Okay, so concatenate these 3 tables together. Concatenate these 3 tables together is the expected output of this example. Okay, if we put them into a 2D view, it will be something like this. Okay, and yeah, you can link any cell or any part here within the corresponding cells or columns or rows within this 2D view. So it's kind of straightforward, and you can try the 3D cube by yourself. Also, I mean, you can discuss this on the forum. All right. Okay, so that's all for the rollup, and we will quickly go through the MOLAP, the multi-dimension OLAP implementation. Okay. So essentially, this is a array-based multi-dimensional storage engine, and we will introduce the advantage and disadvantage here, but I won't explain in details. I will introduce the detail of this multi-dimensional storage engine. Then you will be able to figure this out by yourself. Okay, so the good thing about this array-based multi-dimensional storage is that the size is small, especially for the dense cubes, and it is fast in indexing and query processing. But the bad thing is the scalability and the conversion from relational data. Okay, you will see you will be able to figure out why after you know how it works. Right. So a multi-dimensional array. Let's say this is the data. This data is more like from the relational database, right? So we have 2 dimensions, time and item, and this is the measure, right? The dollar sold, and for the first step, we do the mapping. So we know that for time we have 4 different values: Q1, 2, 3, and 4, right? So we map them to 0, 1, 2, 3, and for item we have say 4 different values: home, entertainment, computer, phone, and security. So the values are 0, 1, 2, and 3 as well. Okay, this is the first step, and then okay, we can have a table like this, right? Instead of using the specific value of Q1, Q2, and so on, we use integers here. Okay, we remain for the dollar sold, it remains the same. It remains the same. So you can think of apparently this for this step, we have significantly reduced the space we need to store such kind of query already. I mean, because previously we need to store the strings, okay, and for each string, the space is depends on the length of the string, and it could be very large. Now we convert it into just the integers, okay, just the integers. So for example, here we have for each integer, let's say we have 4 bytes, right? For each integer, this is 4 bytes. So basically we would have 12 bytes for each transaction, and we have 16 transactions. Okay, so this is what the total space we need to store such a table. All right, now we further do a injective map from cell to offset. So basically we apply a function to convert a combination of time and item to a single value. Okay, as long as this function is, as long as this encoding, so basically we encode time and item pairs into an integer. So as long as this encoding is unique for different time and items, and you can decode it, okay, it can be used here, right? For example, if we can simply, because we know that item is from 0 to 3, so we can use 4 times time plus item as the offset. We call it offset, or the address of this time item combination. Okay, so we have 0, 4, 8, and so on and so forth. And for each of the offset here, for example 5, we can simply decode it into time and item combination as a 1 and 1. Okay, then we can actually use these 2 columns to store the whole array, or the whole table. All right. So for each offset, say we have 4 bytes, so it's 8 bytes times 16 times 16. So this is so we further by doing this, I mean we further reduce the space we need. Okay, and you can think of, because currently we only have 2 dimensions. Now if we have 3 dimensions, say then here we probably will need say 16 bytes, right? But here we still only need 8 bytes. So as long as the dimension increases, we will gain more. We will save more space by using this idea. Okay. So furthermore, say if the table is dense, by dense is that for each offset we actually have a corresponding measure here. Okay. On the other hand, this is a sparse case where, as you can see, we only have two records. Okay, and they correspond to 1 and to 0 and 15, I guess. So in this case, it is a sparse case. So for dense case, let's say we have all the offsets here, or say major, or usually say more than half. Okay. For example, if we really don't have the measure for offset 11, we can actually put a 0 here. But here is like a perfect dense case. All right. So if it is dense, we only need to store the sorted slots. We're sorted by the offset. Okay, so which is just this column, as you can see here. Why? Because we know this column for any, for example, this 952, for any cell of this column or of this array, we can know that it is the sixth cell in this array, which means its offset should be 5. Okay, should be 5. So we don't really need to store the offset as long as it is dense. Okay, and by doing this, we can further reduce. Previously, it's 8 bytes times 16. We can further reduce it to 4 bytes, right? Times 16. So this is what we do for the dense case. Now, what about the sparse case? Right. So for sparse case, we have the same table, but many rows are deleted to make it sparse. Right. So we can similarly do step 1. We have this. We do step 2. We have the offset. So it's 0, 15 as 2 offsets, and 605 and 580 as the measures. Okay. Now we actually have 2 choices to handle this, and let's see which one is better. So first choice is that we actually record the offset and the measure. Okay, and the second choice is that we still keep a dense multi-dimensional array. But for those who has no has no values, we simply put a none here, or you can put a -1. If the measure must be larger or equals to 0, you can actually put a -1 here to indicate that, okay, here it does not have a value. Okay. Now, if we do the computation for the first choice, right, we have 4 bytes for offset, 4 bytes for $. So we would have 8 bytes times the number of records, which is 2. Okay, so it's 16 bytes. But for the second choice, for each of them we have 4 bytes, but we have 16. The length of the array is 16, so we would need 4 bytes times 16, which is 64 bytes. Okay, so apparently the first choice is better. Actually, it really depends on the number of records within the table. Okay, at some certain point, this 2 choice, the space will be the same, and then the second choice would actually have a smaller space. Okay, and how to decode a slot. It's actually using a similar way, right? Because we actually reserve a space or a cell for those who has no values. Okay. So here is what we have just shown, and multi-dimensional array is typically sparse. Okay, so we need to carefully choose which one to use. It depends on the situation. Okay, and for the hybrid OLAP, it's actually a combination of ROLAP and the MOLAP. So basically, we store all non-base cuboid in this multi-dimensional array, and we assign a value for all, right? But for the base cuboid, we still use the ROLAP to store it. All right, so that's pretty much all for today, and also it's the end of the data warehouse part. For the takeaway messages, I think the most important thing, we need to know how to model a data warehouse, which we need to know what are the facts, what are the dimensions, what are the hierarchy structures of the dimensions, right? And what are the measures for the fact. Also, what is a cube, the lattice of the cuboids, and all these are the conceptual level of a data warehouse. And for the logic level of data warehouse, we have star schemas and some of its variants, right? And also, we have different types of queries to answer, right? And for example, roll up, drill down, pivot, slice, and dice, right? And for the physical level, we discussed some techniques on query processing, right? Especially the index and the aggregations, right? For index, we have bitmap index, join index, and star join. For aggregations, we mainly introduced BUC, okay, the algorithm to compute the cuboids based on the base cuboid, okay. And finally, we have discussed the multi-dimensional array, or say array-based multi-dimensional storage engine, which is MOLAP. How do we store the data within a much less space usage, and also support the kind of queries and operations, right? So that's all for the data warehouse part. From next week, we're going to discuss clustering. We will do classification first. Okay, so it's about data mining. Okay, so that's all for today, and today should be the deadline of lab 1, and we will release lab 2 very soon. It's about the implementation of BUC. So please do it as soon as possible. Okay. Okay, so that's all for today. See you next